Okay, in the interest of time here, trying to stay on schedule, probably should start going. So everybody had a good evening and good morning. Of course, after swallowing this, might be a little indigestion in there. But so there's some handouts here, which are basically the slides I'm presenting. So if anyone doesn't have one of these and wants one, there's some up here and there's some over here. So. Yeah, my name is Frank Spera. I actually am a professor here at UCSB in earth science. And Matt asked me to contribute to CIDER this year and to talk a little bit about melting, kind of the thermodynamics of melting. So basically it's a tutorial. I'll try and throw some things in about the deep earth and what we know and what we don't know about melt silicate liquids at very high pressure, high temperature conditions, for instance, core mantle boundary, which obviously is a topic of intense interest for this group. So this is a brief outline of what I'm going to do here, and all the notes you should have. Just talk about melting in the earth, where and how. So we know, the bottom line is we know actually quite a bit. We need to know more. Melting shallow earth, say from 0 to 3 GPa, 0 to 200 kilometers. We understand the phase equilibria. We understand the thermodynamics of those liquids pretty well. And we could do a lot of things, and I'll give you an example, right? And then there's the question of melting in the lower mantle. And that's far more terra incognito. And so we'll mention some ideas there. So basically the structure is to talk about the fundamental thermodynamics of it, melting. Melting is a phase transition, particularly important one in terms of the Earth, because when melts are generated, if they're buoyant, they're not necessarily always buoyant, but if they are, they advect up. And when they advect, they transport heat, and they transport unusual composition. So very important component of planetary evolution and planetary dynamics, actually. So I'll just talk about the basic thermodynamics of melting a little bit, give you kind of the full Monty treatment on the upper mantle, some melting in the Great Basin, show you how we could actually model things, and then present some ideas of the lower mantle using a much more simplified system, drawing on, by the way, all sorts of research here. And the conclusion there is this. And then the next question is, well, lower mantle is still problematic as far as melting. What information do we need? How do we get that information? I mean, because it's the people in this room, the postdocs and the graduate students that are going to complete this agenda, right? It took us 100 years to be able to do this pretty well. Starting actually 100 years ago, very much today. N.L. Bowen wrote a very famous paper, 1915, 1916, applying thermodynamics and phase equilibria to silicate liquids, silicate systems. And here we are, fast forward a century, and we've kind of roughly completed the Bowen agenda for the upper mantle. Now, the next century is going to be that same thermochemical agenda for the lower mantle. I mean, that's the way I see it. What information do we need to get there? How do we get it? Right? And then I'll sort of draw a line here and just talk about some basic chemical physics, heuristic melting models. How do we predict the melting point of a phase as a function of pressure? Calcium perovskite, high pressures. Is the melting curve straight? Does it go this way? Does it go that way in T-P space? And so these are some old ideas. Go back to 1910, Lindemann melting. And the SG melting, and so kind of discuss that a little bit. And the significance for this group, I think, is the relationship between two thermal gradients. One is the isentrope in the mantle, right? Convecting mantle, temperature gradient in the interior is basically isentropic. We usually say adiabatic. That's not really correct. It's adiabatic and reversible, which means it's isentropic. But anyway, we just say the adiabatic. It's really the isentrope. And then the other gradient is the Clapeyron slope. That's the melting curve. So both of these things are the TdP. One is at constant S and one is at constant G. And the relationship between those is absolutely critical to see if melts form and if those melts rise or actually sink. All right. So get into that. And then I do a little plug for this technique called molecular dynamics, because we want to understand these properties of these liquids at very, very high pressures, and well, a couple 100, 150 GPa, that sort of thing. This technique of molecular dynamics is a method by which we can actually not only obtain thermodynamic properties of silicate liquids, which is needed to do phase equilibria, not only to obtain transport properties like thermal conductivity that Quentin talked about yesterday, viscosity, diffusivity, transport properties, but also via molecular dynamics we can actually visualize, see the structure of the liquid, right? SiO2 liquid, how are the Si's and the O's arranged? And it turns out that pressure has a profound effect on the structure of liquids, silicate liquids. And that's really the key. That's the microscopic insight, right? And then the thermodynamics and the transport properties follow from that. So it's a really exciting connection, and we're just beginning to work on these liquids at these pressures, right, at very high pressures. And then some more nonsense here. And then finally at the end, talk a little bit about the role of water in this business. A little bit of water goes a long way in changing the melting properties of silicates. And, it's estimated that we may have 2, maybe 10 oceans of water in the Earth's mantle. Where is that? Is it in the transition zone? Exactly where is it? Is it basically distributed in nominally anhydrous phases, like 50 ppm in olivine and 50 ppm in magnesium perovskite and so forth? Or is it more structurally bound in ringwoodite as a percent or so? So water is extremely important. And then at the very end, I'll just talk about the speculation that we've been thinking about a little bit on the structure of silicate liquids at really high pressure. And it's kind of a cool little thing. May be right, may not be right, but anyway, I'm going to throw it out there. So any questions, just go for it, and we should start in. So melting on the Earth, where and how. It's an important part of the mantle of the Earth engine, right? Basically, 10 to 15% of Earth's heat flow is associated with magma, coming from one depth to near the surface. It's an advective transport of heat. And that turns out to be, when you do the balance, about 10% of the heat flow, which mainly comes, of course, from plate cooling. So here are the basic environments where we have melting, diverging plate boundaries, something like 20 cubic kilometers per year of magma generated, right? That's generating oceanic crust, right? Erupted, intrusive plus plutonic plus extrusive plus intrusive, about 20. Converging plate boundaries, the flux is less certain. Earlier estimates, which I'm guilty of, gave numbers like this, but a later estimate, and there's some references here, show that we might have been off by a significant factor. It may actually be much higher. But at any rate, it's something on the order of maybe 10, 15% of the diverging flux. So 20 cubic kilometers here, maybe 4 or 5 in here. If you average these, why not? Take the geometric mean of these two numbers. Intraplate oceanic island basalts, right? The stuff that mantle geochemists love to talk about. It's probably about a cubic kilometer per year, right, of magma generated there. This is a much more uncertain number, and it would be great if someone here at some point, maybe this summer, starts to look at this. And I think you could do it. I mean, we know the hot spots. It's just it's not real sexy work, but you just got to go around and look at the various hot spots, 50 or 60 of them, and look at the history of these particular volcanoes and start to look at, from the bathymetry and from the topography, actually get the volumes of these. And a lot of times there's some age information. Yeah?
So from what I learned, I heard that 90% of Earth's heat is lost through mid-ocean ridge system. But so you're saying that only 10 or 15% is lost through that?
Yeah, I would say probably 90% of the Earth's heat, presumably through the cooling of plates, which includes the stuff on the ridge, right? I mean, it's plate cooling, right? Because the plates continue to thicken as you move far away from the ridge. Right. So that's the heat loss. Yeah.
Jonathan? Would the OIB number or the intraplate number include large igneous provinces? Obviously, there aren't any right now.
Yeah, it would. There are, like, when I made these numbers, I just looked at the ones that there are today. So, but yeah.
I guess how much of a, if there was one going off, how much of a contribution would that be?
Yeah. Well, they contribute a lot. They're about, they're on the order of a, they could be up to, like Hawaii today is a tenth of a cubic kilometer per year. The LIPs can be 10 times that. Yeah. For their duration.
Onton Java was more than 20 cubic kilometers a year.
Onton Java is more than 20?
Was more than 20 cubic kilometers.
But I mean, it's a very short, period, right?
Yeah, that's right.
But I mean, the whole, what's the whole rate over the beginning to the end of to today of Onton Java? It's probably on the order of a few cubic kilometers per year, would be my guess. I mean, the problem is, you're looking at a discrete process. So you look at something in a decade, and you have a huge amount of stuff coming out. But these are geologic time averages, basically. Okay, so yeah. Anyway, so what's the mechanism of melting here? Well, the conventional wisdom, which is pretty valid, I think, for melting at more than OIB is basically this concept of decompression melting. So you're taking a parcel material, it's at some temperature and some pressure, it's got an enthalpy associated with it. It's coming up because it's buoyant, decompresses, comes to lower pressure, and some of that enthalpy is used to provide for the phase transition. So you melt some of that stuff. So that's decompression melting, certainly important in Moab and Oib. For island arc magmatism, EM, the idea is that it probably has more to do with triggering of volatiles. So everyone knows that you erupt stuff on a ridge, you hydrate that, right? You put what? The whole volume of the oceans through the mid-ocean ridge every 10 million years, something like that, through oceanic crust. So you profoundly alter oceanic crust, and that rides along and it subducts, and that subduction, that stuff going down the hatch may be a green schist, maybe amphibolite facies, right? And there's also some sediment, so there's plenty of water around. Typical green schist has, 4, 5, 8% water in it, something like that. And that goes down. There's dehydration reactions in that downgoing oceanic crust, and it liberates H2O and other volatiles, and this stuff rises into the wedge above the slab, and that lowers the solidus of the peridotite that's there. Right? So that's volatile triggered melting, and then that magma evolves. And then a fourth source of melting is heat effective melting, right? HAM, right? Hart and Matt, okay? That's for Matt Jackson. Anyway, we have to have acronyms, right? So the basic idea here, and this is probably how a lot of the crust can melt, right? You have magmas generated in the mantle. This stuff comes up. It hits the moho, hits density horizons. It stops its advective movement. It cools. It crystallizes. It delivers its latent heat to the overlying crust. If that heat is sufficient, it can partially melt the lower crust, the upper crust. So that's a kind of a standard mechanism when we think of melting. I want to melt this stuff, add some heat, right? It's quite different from this, quite different from that, right? This undoubtedly occurs and may be the main mechanism of crustal heating. Okay, and then we could talk about the great unknown here, ultra deep melting. We have the ultra low velocity zones. Does that melt? Does that not melt? What are the composition of these melts? And some people think they're dense. That means they're not going to be particularly mobile. They're presumably gravitationally stable over geologic time. Is there any entrainment of that stuff? Are they necessarily dense? I'll show you a phase diagram that suggests that depending on the bulk composition, they may not be. And that's interesting. And this is critically important for this crowd because of the OIB connection. I mean, that's the understanding what this CIDER is all about, really. Right? Trying to get the geophysics to work with the geochemistry, or at least outlining the problems. And this is relevant not only on Earth, but could be relevant for other large super-Earth planets, right? And in my personal opinion, the future of igneous petrology, if we're really going to see this fusion between igneous petrology, which comes with this hammer and knapsack tradition, and geophysics, tomography, and other aspects of geophysics, I think silicate liquids could really provide that linchpin, because you've got to understand mineral physics, thermodynamics. You have to understand classical petrology, phase equilibria, and you've got to understand the geophysical aspects of that problem. So it's like the Father, the Son, the Holy Ghost. That's, and I feel that's where we're going as far as igneous petrologists. We need to start worrying about these things at really high pressures. Okay, so. I tend to go too slow, so I better speed up here. I'll never make my deadline. So, thermodynamics of melting and basic liquids. And so let's just consider, so this is kind of the tutorial part, consider a phase change. Now, of course, we always want to be thinking about multi-component, multi-phase systems, right? And that's critically important. The Earth is, look, there's 91 naturally occurring, elements, right? Take out technetium, one of those bizarre elements that's only found in the sun. But and then we're dealing with that. We're dealing with the whole periodic table all the time. Obviously, there's major elements, there's minor elements, there's trace elements, right? And then there's isotopes. Okay. So let's just consider how you basically look at this phase transition. So the way I'm setting this up is, let's just imagine we have, for a start, and we'll go back and forth here, a one component, one phase. Right? So we're just looking at the melting of water, ice to liquid. Except I'm looking at the melting of CAMG Si2O6. Don't worry about it if you're not a mineralogist. It's a monoclinic pyroxene. Pyroxene is a very abundant phase in the Earth's upper mantle. Right? We have orthopyroxene, we have clinopyroxene. This is clinopyroxene, and your friends in petrology might call it augite. So it's a very common phase. When you go pick up a mid-ocean ridge rock, a gabbro, it's half plagioclase and half this stuff, basically, augite. It's not exactly CAMG, there's solid solution, but anyway. So it's just a common phase. And so how do we go about figuring out when the stuff melts? Pure diopside, function of pressure. The way you do it is you write a reaction. First thing you do, if you're a chemist, you write the reaction. Any reaction that conserves mass is okay. It may not be the actual mechanism, right? But it doesn't matter, right? You conserve mass. That's the beauty of thermodynamics. You don't really even have to believe atoms exist, and you can do thermodynamics, which is kind of cool. And then if you believe they do exist, you can get a lot of insight, actually, work it backwards. So how do you approach this? You write the reaction. Solid goes to liquid. What's the constraint in thermodynamics? The constraint is that this quantity called the Gibbs free energy, which is the quantity, the energy quality or quantity potential that's minimized at fixed temperature and pressure. So if you want to know what the status of this carbon is it graphite? Is it diamond? You basically ask the question, what, given this bulk composition, carbon, given a P and a T, what minimizes the Gibbs energy? And that, whatever phase minimizes that Gibbs energy will be the phase present, right? So at low pressures, it's graphite. Then there's this line in PT space in which graphite equals diamond. And then at higher pressures, for instance, at fixed temperature, diamond stable. And you could just visualize this in terms of the free energy of these phases. And you look at them, and there are these hoops, and the one with the lowest hoop is the one that's stable. And so the Gibbs energy is 0 at equilibrium, when solid exists with liquid, ice with water, diopside liquid with diopside crystals floating in it, equilibrium situation. How does that depend on pressure and temperature? Well, here it is in all its ugly or beautiful glory, right? It depends on things like the enthalpy of formation of the material, the enthalpy of the reaction, the enthalpy of fusion, heat capacity, an integral there, the entropy difference between the liquid and the solid, the heat capacity difference between liquid and solid, an integral over the delta V of this reaction, the change in volume, essentially the change in density of solid crystals versus liquid, right? And notice this is an integral over in pressure, right? And that presents some problem. And then we account for the fact that this dioxide crystal is not pure CaMgSi2O6, and the liquid's not pure CaMg2O6 if it's melting to form of the salt, right? You have crystals of pyroxene in equilibrium with this liquid. We account for all that off composition stuff in these activity terms. At any rate, the fundamental expression is here. This is it. This is it. So it gives you the agenda. What do we have to know to do this stuff? Well, what data do we need? We need to have the enthalpy and the entropy change of this reaction at some reference pressure and some reference temperature. Okay? We need to know the heat capacity difference, right? And then there's ways you could worry about that. You can at really high temperatures there are these limits. The Dulong-Petit limit and the isochoric heat capacity, it goes to a constant. And then we could use standard thermodynamics to convert this isochoric heat capacity to an isobaric one. This is a detail. But the only thing I want you to pull out of this is that you'll notice that to make this conversion, the volume appears, right? So the status of this is that we have enthalpies and entropies on a lot of compounds under reference conditions. We have expressions for the heat capacity at low temperatures. We're a little bit deficient at really high temperatures, but there are some pretty good approximations that can be used. We also can compute some of these parameters, like heat capacities, for instance, by molecular dynamics simulation. So we have some of the thermal part of this. The problem comes in really with the volume change. And there's a couple of issues associated with that. So we need to know the volume, the molar volumes of the solids and the liquids in this reaction. And we have to be able to integrate that. So we have to know how delta V depends on pressure and temperature. And this, at really high pressures, this gets more problematic here. It turns out that to about 2 or 3 GPa, you can get away with a very simple linear equation of state here. So that just says that the volume of either a dioxide crystal or the liquid is essentially linear with the expansivity and isothermal compressibility here. And this works actually pretty well, maybe 2-3 GPa, right? That's really key because it's a very simple expression. You can integrate it and you can run with it. At higher pressures, we get into the mineral physics domain, right? So at higher pressures, a simple law like this breaks down, right? The materials don't have a constant expansivity or a constant compressibility. It's a more complicated business. And I'm sure that there are lectures, one yesterday and many more, about mineral physics and this whole business. The way this is traditionally treated is to break this up. You start dancing a little bit here. You break it up into what's known as an isothermal equation of state, and then you add a thermal correction to that. So this sort of starts with Bridgman and Birch and all those guys, and other people, right? It's cottage industry for mineral physicists to do this kind of stuff, condensed matter physics people, to work on good equations of state. So what is this? This is just a relationship between the pressure and the volume. And this is done along an isotherm, right? So at some temperature, this is the relationship between volume of the material and pressure. It involves the compressor, essentially, the bulk modulus, or the 1 over beta here, the isothermal bulk modulus, and the derivative, right? So we have these different flavors, these different relationships, and people argue about these and propose more. There's must be tens of these. I don't know. I'm not an aficionado of these. Probably someone like Quentin would be. But we have all these different ways of doing it. The Venet, so forth and so on. And so that gives us the isothermal part, because what we're after is a relationship between pressure and volume, right? So that gives us this part using one of these. And then for the thermal part, there is this thing that probably goes all the way back to Grunison and me, and I think Anderson at UCLA did a lot of stuff here. You make this thermal correction, right? So now you're trying to put temperature back into one of these isothermal equations of state. And the way you do that is you just augment the pressure by this other term called the thermal pressure. And then there's various ways of doing that. And you make certain assumptions. The PdT at constant V is, by definition, alpha over beta, or alpha times kT. So that's absolutely valid. And you can write that in terms of the Grunison parameter, the isochoric heat capacity, and the molar volume. And then you integrate this. And so if you say that alpha K is not a function of temperature for temperatures above the Debye temperature, which is kind of critical temperature, then you can integrate this and you come out with the form of this equation after the integral, and maybe on the next page.
Frank, before you go to the next page, 2 quick questions.
Yeah.
Why did you call this is an approximation? It seems like if you have the isothermal part and then a thermal correction, you've accounted for everything.
Well, it comes in here. I think when you do this integration, you don't really know the dependence of alpha and kappa, right, on temperature. So you you make some assumptions, and you say it's a constant at temperatures above the Debye temperature. It's not exact. It's not
Second
exact.
question is, could you remind us what the Debye temperature is?
Yeah. So the Debye, crystals are vibrating, and it's Quentin can probably answer better than I can. It's basically when those vibrational states are occupied and there's saturation of vibrational states, right? Like at 10 degrees Kelvin, you're not exciting certain vibrational states, but the Debye temperature is kind of a temperature where a large fraction of those are excited. Is that kind of?
That's close enough.
Yeah.
I would make one other comment also, which is that there are alternate ways to get up to high pressure and temperature than purely separating pressure and temperature as you've done here. You can also define things that are important for this room, like the adiabatic bulk modulus, also very similar to the isothermal bulk modulus, but often a little different. Often the derivatives are a little different, but correctable, so you can track it up in adiabat is an alternate way of going to high PNT.
Yeah.
So are these all empirical relationships? Yes.
There's a certain degree of empiricism in them. I think
Based on finite strain.
there may have been some physical insight into these, kernel of truth, and then it becomes a fit problem. How do we get this data? You go into the laboratory, you squeeze something, you measure its density.
Just to note, some of this we're unpacking in this afternoon's tutorial.
Yeah.
I'm busy uploading a series of notes that outline the steps to derive the pressure volume for Thermodynamic equation of state, which you see up there, and then different approaches to get at that thermal property, from very simple empirical approaches to the statistical mechanics analysis of the Debye temperature.
Great.
So it should all be in the notes for this afternoon.
Good.
And maybe a comment perhaps is that really what one is getting at is the free energy of the system, right? Like one really wants to define all the parameters that define the free energy, with pressure being a result of the thermal contribution, the elastic, perhaps electronic and harmonic terms.
We have to keep our eye on that apple. That's what you want. You want the delta G for reaction.
Free energy.
Or if you get the Helmholtz energy, you could operate. I mean, that's a beautiful thing about thermodynamics. These things are linked, but that's what you want. Yeah, and I was just doing this in the context of that integral to get the delta G. It's an integral V dP. Okay, we got to know delta V, and then how do we get that? So, but yeah, I'm doing mineral physics for sixth graders
Another
here. So,
question.
A really simple question. What's the Grunheisen parameter?
I'm sorry, say again.
What's the Grunheisen parameter?
That will also be into this one. That will also be this one page on the Grunheisen parameter for this afternoon.
There is a one-sentence answer to
Is there a
that,
one-sentence answer?
which is if you heat up a sample at constant volume, is the pressure change associated with heating a sample at constant volume?
yeah,
Right.
and that's the source of the correction, essentially, in the Grunheisen.
I have another one-sentence kind of definition. So you can also think about it as the thermodynamic dimensionless parameter that balances, in some ways, balances the PV energy and the TS energy. And so if you think about it as a geodynamicist, that's another way of looking at the Grunheisen parameter.
Okay. So,
You spend a lot of time telling us about how we're going to get the volume changed, but in that Gibbs free energy, there's also change of entropy and enthalpy. How are those numbers ever going to be known?
the enthalpy and
The delta H, the delta S.
experiments.
Okay.
Or molecular dynamics can give you that. But basically, it's thermodynamics is the structure, but there's no life in it until you put real numbers in. I mean, you need measurements. Right? Okay. So, yeah. So, where were we? Anyway. Yeah, so this is actually, speaking of molecular dynamics, this is this is basically here to point out that, let's think about dioxide liquid, okay? And when you think about it at low pressures, if you look at that liquid, you do spectroscopy, you find out that if you look at the structure of that, and that is the O around the central silicon, and we all know that silicates are based on the silica tetrahedron. Right? So all in crystals of dioxide, all of the silicon has 4 next nearest neighbors of oxygen. And then those tetrahedra are linked in a chain. Okay. In the liquid, though, notice that this purple curve is the fraction of silicons that have 4 oxygens around. So this is the tetrahedral unit in that liquid. And you see that it's 80%. At low pressures, 80% of the silica tetrahedra are 4-fold. Oh, then you have a few of these. Here's a 5-fold, and a few even 6s maybe. But you're really dominated by these guys. And all these numbers obviously add up to 1. But, and this is the point here, this is along an isotherm. You start squeezing this liquid. Unlike solids, which you can squeeze and elastically they deal with that squeezing, and then they undergo a phase transition. Like silica, polymorph, right? You start squeezing it, it densifies, but it's still alpha quartz or whatever. And then at some critical pressure, boom, it goes to coesite, right? And then finally it goes to stishovite, where the silica is in 6-fold coordination. Liquids show those kinds of behaviors in a continuous way, a more gradual way. So as pressure increases, the fraction of the silicon atoms that have 4 oxygens around them, tetrahedral polyhedron, goes down dramatically, right? And by 100 GPa, it's diddly squat. Whereas the 5-folds, this is bizarre stuff, a 5-fold coordination. It's actually a trigonal pyramid, right, structure. And you see that actually rises and hits a maximum, and then actually starts coming down. Whereas the 6-folds, right, like in stishovite, 6-fold, actually monotonically increases through here. So the point here is just to make it clear to you that pressure has a profound effect on the structure of silicate liquids, and that is really the key to understanding their properties if we want to know what's going on from the microscopic point of view. Here's another way of looking at it. This is the SI around O. So now you take O as your central atom, and you say, how many SI atoms are nearest neighbors to this central O? What fraction of these O atoms have 2 SI as nearest neighbors? That's that. What fraction of these oxygens have 3? Ooh, that's the structure of stishovite, actually. Every oxygen has 3 nearest neighbors of silicon. Every silicon has 6 nearest neighbors of oxygen. That's increasing, right? And what fraction of the oxygens have 1 nearest neighbor of silicon? That's falling off. So you see the densification of the liquid occurs, and you can monitor it by looking at the structure of the liquid, and you see that it's a continuous change. Solids don't behave this way, right? They change a little bit, but then boom, at some critical pressure, they jump up and they change a lot.
Why do you stop at 100 GPa?
I'm sorry?
Why do you stop at 100 GPa?
Why did I stop at 100? Quality of the potential made me a little nervous, right? Yeah, we'll talk about the 2 different kinds of molecular dynamics. Yeah, I have in some of the papers we do go out further, but This is a very discerning group, so I didn't want to commit any mortal sins. So here's the typical question. Typical question to kind of summarize. Here's what we want to know. Given a bulk composition, right? You guys know what a bulk composition is. Nothing to do with minerals, nothing to do with anything other than just specifying the bulk composition of a material. Right? What's the SiO2? What's the MgO? What's the FeO? What's the bulk composition? Given a bulk composition and given a pressure and temperature, what phases, what amounts, what are their compositions, and this includes liquids, at a given PT? I mean, that's the fundamental problem. And so what I want to address here is how far along are we in addressing this problem, and break it up into low pressure, upper mantle, which I'll have to skip over, give you some details, and then try and address this in a deeper manner. Okay, so at pressures less than about 3 GPa, we can, there's been a lot of work here starting going back to the days of Bowen, and then fast forward to the 70s when this character, Mark Gurso, really took it upon himself kind of single-handedly in the beginning to develop computer routines based on a thermodynamic database to minimize free energies and basically be able to solve this problem. Here's a prototype. You give me a pressure and a temperature and tell me how 10% melting, and I'll tell you the composition of that liquid and the composition of all the phases that are in equilibrium with that liquid. And so what I'm going to be discussing here is some of these models. They work to about 170, something like that, kilometers. It works pretty good for ultramafic to very silicic compositions. So if you're subducting sediment and you're down at 150 kilometers and you've got a wad the size of this building of some old, Ganges delta that got subducted, it's got the composition of silicic stuff, you can address questions if that stuff starts to melt, what's its composition? What's the input to this model? The inputs are basically the standard thermodynamic properties of the minerals. For the solid solutions, we have to know the activity composition relations, because again, we don't have pure CaMgSi2O6. We have Ca with a bunch of other stuff, comma, Fe plus magnesium plus other things. We have solid solutions, crystalline solutions, and we need to know the activities of the idealized components in these solutions. So that's called AX theory. We also need to know, and this is really what Gurso did, which was, I think, a big step forward, is come up with a model for the free energy of an arbitrary composition silicate model. The function composition, X, pressure and temperature. Right? So if you have all that stuff, and the way you get this is by doing thousands, literally, of experiments where you take a little bead, platinum bead, and you put some silicate liquid on it, and you have a little crystal of olivine that's in equilibrium with that liquid, and you quench that, and then you analyze the olivine, and you analyze the liquid, and you write the statement of equilibrium. Fe2SiO4 solid goes to Fe2SiO4 liquid. And you do this thousands of times. You take all that stuff and you invert it, and out pops the enthalpy of formation of all these end members, the entropy, third law entropies. You don't get volume that way. You've got to go for other data. And for crystalline solutions, you can get the activities. So, and the free energy of that liquid. Right? So it's a laborious process. Started around the mid-70s, actually 1982. And it's continuing, and it's embedded in this MELTS algorithm. So for the geochemists here, they probably know about this, petrologists. You can do this sort of stuff. Does it have limitations? Of course. Things like you would like to incorporate, so this is for the petrologists here, better activity composition models for the amphibole. Amphiboles are a little dicey in MELTS right now. Sheet silicates, phlogopite, biotite, things like that could be improved. And, we don't have in it yet, Mark does not have in it yet, certain minor elements in certain phases, like chrome and pyroxene. Sulfur is a component. It's limited to H2O, CO2 fluids. And it does not allow for something that may turn out to be important, and that is that rocks dissolve in water CO2 solutions at high pressures. And there may be complete solubility between so it's not like you have a silicate liquid in equilibrium with vapor. You may actually have a single phase solution that may have 30 or 40% dissolved rock in it. At any rate, it's got some limitations, but it's fundamentally very successful. It's a die-in-the-wool tool that igneous petrologists use all the time now, right? So I don't know if I have time to trace out this problem. It's in the notes, but I wanted to run that out. Let me just tell you what the problem is, and then I'll tell you what the solution is and skip over how we do it. But for instance, you're out in Nevada and you're working on some quaternary alkali basalt flows. So anybody flown across the U.S., you see these little cinder cones. These are quaternary. So this is one that erupted 80,000 years ago, very close to Las Vegas. Unfortunately, it didn't flow into Las Vegas and plane it. That's my editorial opinion here. And so how do you go about this? Okay, we know that this is partial melting in the mantle. We know the partial melting of some sort of a peridotite. And the questions are, what was that peridotite? How much melting took place there? At what pressure and temperature? And then as this magma started to ascend, did it undergo any change? Are we seeing it in its primitive form, or did it actually grow some crystals on the way up and change composition? And then very near the surface, it becomes vesiculated, because this basaltic cone in Nevada has a third of it is tephra, right? Vesiculates, the magma breaks up, so they're volatile. So you'd like to understand the complete petrogenesis of this thing. Does it work with trace elements? What trace elements you kind of know about the mantle? So how do you do this? So you basically do it in steps. You first look at, make some guesses about what the bulk composition may be of the peridotite, and you study partial melting. You study it as a function of pressure and redox condition and extent of melting. And you generate some liquids. Then you take those liquids and you let them come up, and you do polybaric or isobaric fractionation. And the point is, you know what you want, and you perturb your variables to get it, basically, right? And so, in a little more detail, this is just a little picture of this. This is this big cinder cone. It's called Lathrop Wells. You see a bunch of lava flows here. This is a monogenetic alkali basalt cone. About 1/10 of a cubic kilometer of stuff came out, like probably in 2 weeks. And you can test for whether the melting occurs by batch melting or fractional melting. You could test for the composition of the peridotite. You could test for pressure. So we're running this code to do this calculation with different assumptions, seeing what the effects of these different phenomena are. And when you do that, you conclude, and I'm not going to bore you with the details, you conclude that probably looking at a batch melting situation, meaning that the first liquids that form aren't immediately separated from that peridotite, that there's a rheological threshold that you've got to generate enough liquid so that liquid can become mobile. Probably batch melting to the extent of about 10%. So 10% of this original peridotite has turned into liquid. The source composition here is a moderately fertile peridotite, right? It's not tremendously depleted like more mantle. It's got some juicy stuff in there. And that the melting takes place at 1.5 GPa. It's about 50 kilometers.
Question, John?
Is there no degeneracy in these kinds of answers? Is this a unique solution?
These are
How do you
unique
know
solutions.
that?
Yeah.
I mean, it seems like there are a lot of variables and a lot of parameters you can play around with.
Well, I mean, you start going in and jacking around the free energy of formation of phosphorite, yeah. You know, you have a database, and there's uncertainties in the thermodynamic parameters. The codes to minimize free energy is, excellent. That's not the problem. So, yeah.
I guess if your constraint is the final composition that you measure in the tephra, is there only one pathway to get to
No,
it?
there's not only one path. I'm sure there are others. Like, there's trade-offs. So we could use slightly less fertile peridotite and melt it at slightly higher pressure. So that's quite true. There's other constraints the thinking petrologist brings into the game. Like, for instance, there's xenoliths that these magmas bring up. And so we use those to constrain the composition. So, yeah, I'm sort of giving the straight thermodynamic story. But, yeah, no, I think I probably answered you wrong my first statement. So I think you're right. Yeah, there's definitely trade-offs. And I don't mean to say that, Okay, so I'm not going to bother to show you this. You could read these later. You'll probably see your own De La Guerra room or whatever, wherever you guys are staying. And then, so once you form the melting, you can test for things like, okay, we've got this primitive liquid at depth, and we know what we have in the volcano. And what fraction of that liquid actually crystallizes on the way up? So you can test that. And what's the pressure at which the mean pressure at which that fractionation occurs? And these plots are not, I'm not going to go through these, it's just meant to show you that you can explore this question, right? And then when you get your solution, and yeah, it involves some driver concern, it's not robotic yet, then you can go back and you can really do the mantle geochemistry thing and say, okay, I've got a major element solution. I think this was 10% melting of this fertile peridotite, that this magma came up, and that 50% of it crystallized on the way up, and that's the liquid that was erupted. Right? I think that's a good solution because it matches the major elements of my volcano, and it's reasonable. Then we could test that with another layer, and that would be the trace element. So now you have the trace elements are kind of decoupled from the major elements. So you go back with your phase equilibrium, major element, major phase solution, and you test it because you also have trace elements in this lava, and you test it. And that's what this is showing. This is showing the actual range in gray here of trace elements in a spider type diagram. This shows the liquid that is generated in the mantle. That would be at the bottom here. So let's take one of these with a big. So this is the trace element concentration relative to some standard in the liquid that's generated in the mantle, 10% melting peridotite. And then if you have this stuff come up and you do the fractional crystallization part, that drops from T down to the X. Okay, so that's how you interpret this. This is what you had in the primitive melt. This is what you get out at the surface, allowing for the effects of fractional crystallization. And so you can kind of play this game. And I guess the bottom line is, well, let me just do the last step. And since I like volatiles, then you could also address the question of when you look at this volcano, you do see ash forming. You see lava flows and ash. And you could address the question, well, when does this magma saturate? When does it vesiculate? When does it break up? And the way you look at that is you use the phase equilibria to give you a handle on the total volatiles. And the only critical point here is looking at this thing. This is the volume fraction of vapor, which in this case is water plus CO2 in some ratio. And this shows you as a function of pressure. So this is 100 MPa. So what is this? This is 5, 7. Yes, this is like a kilobar. And what it shows is the volume fraction of vapor in this system. So now it's a two-phase system, liquid, vapor, bubbles. And look at the volume fraction here this is the mass fraction of vapor, always rather small. The volume fraction is huge because at low pressures, the gas is expandable, very compressible. The liquid isn't. And so this critical value of about 70 volume percent, that's where the magma vesiculates. It just breaks up. Right? And that, boom, you get your eruption, and you get this ash that forms. Teflon, fallout. And then the magma degasses, and then the later parts of the eruption are these mildly effusive lava flows that come out. So the ash will be covered by the later lava flows. So what am I saying here? I probably spent too much time on it, but we defined we can take a given sample, volcanic rock, we can invert the process and start to make guesses about what's going on, right? So to summarize here, we have this batch partial melting at something like 60 kilometers depth of a somewhat fertile peridotite beneath the Great Basin. It contains small amount of water. And we have redox conditions that are set along the QFM buffer. And the extent of melting is about 10%. And then this magma arises and it fractionates, and it loses basically a lot of olivine and some pyroxene. And it fractionates at a mean pressure of about 30 to 40 kilometers. And this changes the magnesium number of the liquid from 75, which is very magnesium, very primitive, to about 53, which is what we observed. And we can match this target volcano, right? 70,000 years ago is its age. We could estimate the total volume of melt generated by partial melting. And that's estimated to be 0.5 of a cubic kilometer. And if you believe that's 10% melting, you've got some melting volume on the order of 5 cubic kilometers at 70 kilometers depth. Anyway, and then finally the magma saturates at a kilometer. It saturates with volatiles, and it fragments partially, and it erupts, and you get this thing. So, okay, petrology and chemistry kind of works. We can kind of do that for the upper mantle, and that's what you guys probably need to know. Kind of do that now, right? Again, I don't want to push that, but we can. What about the lower mantle, right? Can we do this, right? Given a bulk composition, what phases are present, and what's their compositions, and what's their amounts at some P and T? P is going to be 130 GPa, T is going to be 5,000, 4,000, whatever you choose. Can we do that? Answer. Short answer. No. Right? We can't. Quite. Important question. So people in this room maybe can address this. Why can't we answer this question? Well, we couldn't answer the shallow melting, or the upper mantle melting question until recently. And that's because we didn't have standard state data, activity composition relations, know more about the compressibility that Abby was talking about, and significantly know what the bulk composition is. So what are the minor problems with this? Well, the first problem is, well, what is the composition that we want to melt in the lower mantle? Well, we have guesses, right? But there's a lot of variability, which is, I guess, the core of the problem. What are the possibilities? So-called fertile peridotite composition. So I'm using peridotite in the compositional sense. I obviously understand that mineralogically speaking, at these pressures, the lower mantle now, that whole composition is not expressed in terms of olivine and pyroxene and garnet, different minerals. But anyway, as far as the bulk composition, is it a fertile peridotite? Is it metasomatized peridotite? That is peridotite that's been affected by volatiles that have been sucked out of the descending slab, right? And you throw some volatiles in there, and some of that stuff gets circulated back in. Is it depleted mantle, the famous DMM, right? Depleted Moore mantle, the mantle that results when you suck out mid-ocean ridge basalts. Is it subducted oceanic crust, so-called high-mu reservoir? What about the extent of hydrothermal circulation in that crust, right? Been variably hydrothermally altered. So there's chemical changes occurring there, and that stuff goes down. What about sediments? Sediments are, thought to be, going back to Bill White and Hoffman, pelagic sediments with some carbonates, the EM1 source maybe, or terrigenous sediments, the EM2 source, right? The bottom line is we've got some stuff going down. Old continental crust, is that subducted? Right? The stuff Taco Bell calls meat, is that down there? Right? What is down there? So this is the problem. This is the problem. If you're facing this from the point of view of trying to predict liquid compositions, you've got to know the bulk composition you're starting with, right? We know for the upper mantle, the derived basalt, it's peridotite. Oh, we could shade it, put this in, put that in, but it's a shading. Here, to me, to my limited knowledge here, there's more of a problem. We don't really know what the composition is. Is this the key to the ultra low velocity zone? Is this the key to the low shear wave provinces? Are they, and this is the essence of this whole conference here, right? What are those things? What are those tomographic anomalies? Slowness? What do they represent? Could it be compositional? I mean, I don't know. Maybe it is Taco Bell meat down there, which would actually be a good place for that stuff. Recycling, Okay, so even given a bulk composition, and probably Abby and others here will talk more about this, even given a bulk composition, hand of God, here it is, right? What do we know about the minerals that are present? Well, we know something, right? But we don't know, perhaps enough. For instance, if the bulk composition is peridotic, okay, pyrrolite, Ringwood's favorite word. And then how do you read this? This is depth, so here's core mantle boundary. Let's just go to 2,000. The way you read this is that for this bulk composition, at presumably some temperatures implied here, high temperatures, the magnesiolustite, MgO, FeO, right? Magnesium iron oxide, maybe 10%. Magnesium perovskite, most of it, 60-70%, and then some calcium perovskite. Okay, But if it's a Hartsbergite, more like a depleted mantle, then you have a different mineralogy present, right? You have magnesiowustite and the magnesium perovskite. If it's a bulk composition of more, like high mu, subducted eclogite, right? Subducted oceanic crust, which of course is altered, so this is not quite right. But anyway, then you see you have different phases. You develop a silica polymorph, stishovite. This is some weird calcium chloride structure, SiO2, and this I don't even know how to pronounce. Calcium perovskite, magnesium perovskite, and this is a calcium ferrite phase. It's an iron calcium oxide. So my point here is a couple. One is we don't really know what the composition is. Two is people have made guesses, and we have these minerals. But when you look at these, you realize, yeah, but you know what? It's not magnesium perovskite. It's not pure NgSiO3 for mineral value, right? Let's forget about post-perovskite. What is it? Well, there's solid solutions going on, and so this is for these guys. There was some joke yesterday I didn't quite get about the Birch 1953 paper.
It's that we're all so sick of this in mineral physics.
Oh.
And I'm going to propose as a CIDER project that we do an alternate version of this for seismology, for geodynamics, and for geochemistry. Random collection of red blobs, plumes.
Now we'd like to pick on you guys.
We ran our model till it turned brown. So anyway.
Right. Okay. So I had to
do this for 30 years, at least in my life. Yeah.
It was the first paper I Xeroxed in 1971 when I got to Berkeley. I went to the library and got this Constitution of the Earth's Interior Birch. So anyone here that hasn't read that, should just get it and read it for the young guys. The old guys, okay, that's a different story. Anyway, so so here I was talking about this. So this perovskite is, it's not magnesium perovskite, which we maybe know something about. It's magnesium iron, some ferric iron, probably some aluminum in that big A site. There's some aluminum and ferric iron on the smaller B site. In other words, these minerals, even if we know their fundamental identity, their bulk compositions are uncertain. And that enters into the melting problem, that the activity of this component, the magnesium SiO3 component, is not unity, right? It's less than that. It's diluted. You have to understand activity-composition relations and non-ideality and mixing. And you could say that for the magnesiowustite as well, and you could say that for the calcium perovskite, right? Just to take one of those examples. They're not just pure minerals. We don't really, so that's one issue, right? So I'm trying to say why we can't do lower mantle melting the way we can do upper mantle melting. So one is we don't know the bulk composition. The other is even if we knew the bulk composition, pyrolytic, we need to know more about the AX relations in the minerals. And then very significantly, there's no, that I know about, free energy model for the liquid, for silicate liquids of arbitrary composition at P and T at these conditions. Right? This is the thing that Gurso spent 30 years working on for the upper mantle. And it enables us to do that calculation I showed you earlier. So that's missing. However, don't lose faith. So we can say this, and that's, I guess, obvious to everybody here. Maybe I'm dumb for even writing that down. But anyway, and certainly, it's true here. But we can say something, and we can go to this way of doing science, which is to invent toy models, right? So you could say, okay, we don't really know what's going on there. So let's think of a system silica, MgO, FeO, right? After all, they do comprise 90% of the bulk composition, pretty much, okay? And let's look at phase relations in like the MgO silica join. Very simple Earth now. And then we'll throw some iron in and see what happens, right? So how do you do this thermodynamically in a correct way? Well, you've got to know the free energy of these things. How do you get these properties? And one way, and I'll just talk about Lars Stixrud's et al. where they use first principle molecular dynamics to examine the magnesium silica joint and to study the free energy, essentially, the free energy of these liquids as a function of composition. Because that's what they're adding in here, as a function of composition. And of course, you're getting it also at high temperatures and high pressures. And then you can combine this data, and I'll try and give you an example, with some ways to account for the iron effect, which is tough, because iron has this high spin, low spin transition. You have to worry about that. Then we can compare the phase diagram for magnesium silica at low pressure and at core mantle boundary pressures. And we can see how the topology changes, how the temperatures change, how the eutectic liquids change, because that's the key for melting, how they change. And we can play other kinds of games, like you could potentially have compositional anomalies that you melt and you form one liquid, and compositional and sort of background fertile peridotite that you melt and you generate another kind of liquid, and you can actually mix those liquids at high pressures. So, so this is a phase diagram for magnesium silica at low pressures. One bar, and just let me hit a few things here. This is the magnesium perovskite composition, MgSiO3. This is periclase, MgO, PE. At low pressures, we have this other mineral called olivine, the most abundant mineral in the Earth's upper mantle, above 400 kilometers. Olivine, ancetite, or magnesium silicate, and silica. And what you notice here is a certain topology. Obviously, cannot have a lot of time to go through this, but you see a couple of things. One is, and then this is the diagram, the same system, based on Stixrud et al. And some machinations that I fooled around with, at 135 GPa. So this is core mantle boundary pressure. And you just want to compare these two systems. So this is the change. This is what pressure does to the free energy, seen in a mineral liquid sense. So a couple of things. One is olivine is gone. Olivine's not stable at high pressures. You all know that. So here's the olivine composition. Doesn't give a hoot about this particular bulk composition. The low pressures, it's extremely important, right? Olivine melts here, and there's a reaction relationship and all that groovy stuff that you learn in Geology 101. So suppression of phosphorite. Second thing you notice is suppression of the incongruent melting of magnesium silicate. If you take MgSiO3 at low pressures and melt it, heat it up, it doesn't melt to liquid MgSiO3. It melts to a liquid that's more enriched in silica, and the remaining residue is olivine. It's called incongruent melting, right, of this stuff. That's suppressed at high pressures. You don't see incongruent melting. Something I left out of here, at low pressures, there's actually a big solvus gap here, meaning that you can get two liquids existing, right? I didn't even bother to draw that in. But that's suppressed at high pressures. You don't get that. And what other things do you see? Well, obviously the obvious things. As you go from 1 bar, 10 to the minus 4 GPa to 135 GPa, the melting temperature, for instance, of periclase goes from 2850, right, to 7200. The melting point of silica polymorph goes from about 2000 C at room conditions to 6000. So obviously temperatures go up, right? That's not news. But you also see some other stuff that's interesting. The eutectics, right? So if you think about this, there's basically two eutectics in the system. The eutectic here, and that's this composition, 0.54 of silica in this liquid. And here it's 0.7. So it's actually shifted. Actually, the liquid shifts to higher silica contents at these pressures. This eutectic, which is 1863, and it's point something here, I can't even read it, is shifted also to higher silica composition. So that's kind of interesting. Right? These eutectic liquids shift, go to higher silica content. Silica is going to reduce the density of the liquid relative to MgO and iron. So you see that shift. And I think I have a couple more versions of this. Yeah, so this is just pointing out, you see the migration of eutectic 1 and eutectic 2 to higher silica by 10 mole percent in this case and by 20 mole percent in that case. That's pretty significant. It's a big change in the silica content of the eutectic, the easy melting liquid, the low temperature melting liquid. Right? It's a big change in composition, which will have a measurable effect on things like density.
Frank, is that true at very high pressures as well? That the silica is less dense than the MgO?
Yeah. Okay, and let's see. Right, so examining this in a little more detail, let's imagine we have a bulk composition, and let's use this as our breakpoint. So remember the lower mantle for peridotite is maybe 70% magnesium perovskite, 30% or 20% MgO. So it's on this side, it's on the left side of this composition, right? A bulk composition here, right? Standard mantle. And so if you had a bulk composition here, and temperatures reach this point, you heated that stuff up, that stuff's going to melt, and its liquid composition would be here, right? So you can see if you got this and that, and you're melting it, the first liquid you generate, the eutectic liquid, would be at 4600, and it would have this composition. On the other hand, if you had some of this subducted garbage, sediment, stuff like that, EN2 source, EN1 source, even high mu for that matter, and your bulk composition was here on this side, this is a thermal divide. So this is kind of an important thermodynamic composition here. It's called a thermal divide. We see this all the time in low pressure systems. We have a bulk composition on this side of the thermal divide. We heat that stuff up. The first liquid that's generated is here, right? Quite enriched in silica. And it happens at a lower temperature. Right? So if we have this heterogeneous mantle, and this is a cartoon example here, a toy model, but if we straddled this bulk composition, some places it's on this side of the thermal divide, some places it's on that side, we could form different composition melts. Well, as a matter of fact, at low temperatures we'd only form this stuff, right? And if we could increase temperatures in the same heterogeneous block of mantle to that temperature, then the liquids here would evolve this way, and well, either this way or that way, depending on the bulk composition, probably this way actually, and we can develop some liquids here as well. So there's a possibility of having two liquid compositions of different physical properties, different compositions, different silica contents, different iron contents, different magnesium contents, so forth, kind of coexisting, right? It would be present. And then you want to inquire the density of those liquids, right? All right. So that's what I'm talking about here. You've got these two eutectic liquids, and you could play some games with these things. And if you wanted to do magma mixing, you could go here and find a model for doing that kind of stuff. But at any rate, what about the density of these melts? Well, when you add iron to them, I was just talking about MgO, silica. When you add iron, according to Stixrud et al., that the iron-rich liquid, which he was studying, was on this side of the eutectic, is denser than the surroundings. So it's gravitationally stable, right? However, this liquid, I don't know. I suspect it's not denser than its surroundings. I suspect this liquid is less dense. So, if you had this heterogeneous, subduction, core mantle boundary, from regular peridotite and a big lump of Taco Bell stuff over here, and you raise temperatures, you start to melt the Taco Bell stuff, you might have buoyant magmas. You raise them a little more, you melt the peridotitic stuff, and it's iron-rich, it's denser. You can get some interesting magma mixing that can occur, and you also can get separation here of different liquids. So maybe this stuff is stable gravitationally, this stuff isn't. I don't know. We don't know the answer to these questions, right? Conclusions, right? Conclusion is we're not there yet to do this completely. For deep mantle, we need solid equation to state. We need activity composition relations. We need to know liquids beyond this. We really only have, magnesium silicate in any way, shape, or form. Know about those liquids thermodynamically. We could throw this in as a contaminant, boiling point elevation type routine. It's kind of dicey. But that's what Lars did, and that's what you have to do. But we need to know the effects of calcium, alumina, redox conditions, spin state of iron, right? These are all things. And, better constraints on the bulk compositions. Okay. So this, I see I have a few minutes left, so I will jump to, I'll get rid of the sidebar. Kind of part 2 here.
Question.
Yeah.
Question. So if you have these two different liquids, can you distinguish them by how the trace elements will differ?
Those liquids would have very, very different trace elements. They would have very different trace elements. Yeah. Not only would these, presumably the starting, let's take this very simple model of a prototype next to Taco Bell. And, you have large enough domains so that these are not in thermodynamic equilibrium. They haven't diffused through. The minerals in the Taco Bell are quite distinct from the minerals in the prototype. The trace element abundances in those phases, I don't know what they are, but I'm sure they'd be different. And the partitioning, the trace elements in the liquid are going to be governed by the concentration of the trace elements in the phases that are in equilibrium with those liquids. So yeah, I think you could say they would be different. May give you a way. In a way, maybe that's what OIBs are all about. It's stuff that started in the 80s. Maybe that's what we're seeing. Why is Hawaii, trace element enriched relative to more somewhere? Maybe because it has a small amount of Taco Bell in there. Yeah.
So if Taco Bell melts at low temperature and surrounding mantle is in still solid state, is Taco Bell remains to be a melt, or is it going to react with surrounding mantle and sort of induce alteration of proteolytic
Very good question.
mantle?
You get into the magma transport problem. But yeah, how big is the Taco Bell domain? Is it 10 kilometers, 5 kilometers? Is it the size of this room? Is it the size of the chair? The size of the chair, you melt it, it's going to react with the surrounding prototype. Right? And just induce some metasomatism and change a little halo around that chunk of prototype. But it has reacted with it, so it has modified that. If it's the size of this building, ITP, or the size of Santa Barbara, I don't know. Can you have such big chunks? Well, people, this is Michael's thing about mixing in the mantle. The action of shear reduces the size of a compositional anomaly until it's small, and then you can diffuse it. But I imagine in a convecting system, you could preserve bigger chunks, like if they're in the center where there's not a lot of shear going on. It's a complicated system, right? That 4 billion years of convective circulation. What's the size distribution of Taco Bell clumps? Can they be as big as this building? Or are we talking, meters? It would be an important question to address. And then the other thing is, I wanted to ask someone, and I know there's people here to do this, what do you have to make the viscosity of the lower mantle, say the lower 1,000-kilometer mantle, to preclude any kind of circulation there? If the viscosity of the lower mantle was 10 to the 26 Pascal seconds, would you just have a stagnant lower mantle? Is there some threshold viscosity? And how far away are we from it?
24 orders of magnitude. Right? The Rayleigh criterion, doesn't that give us an order of magnitude estimate?
Yeah. 10 to the 26 is probably not high enough, but maybe 10 to the 28 or 29.
Well, what about, though, if you incorporate the viscosity variation, can't you have a stagnant thing here? And yeah, a high enough Rayleigh number to get circulation with your 10 to the 22, but it's certainly impeded down here, right? People have done those calculations, I'm sure. Yeah?
I was a little bit confused on the treatment, the dismissive treatment of iron. I mean, my understanding was that iron could have a much more profound influence on the eutectic and on the melting temperature. And you said that it sort of treats it as a perturbation.
Well, I mean, that's yeah, I was embarrassed to say that, but that's the way we do it because we don't have the data to really do a better job. But that's what, yeah, so basically, oh, it does affect things, but the way it's been treated, the way Laura's, for example, treated it is kind of, yeah, putting that in and like assuming ideal mixing, and he has a paper and you see tiny deviations of those eutectic temperatures and compositions. I don't know if it's correct, but it's all you can do, right? You haven't done the first principles of molecular dynamics with iron in a liquid. That would really give us the true thermodynamic properties. So you go back to physical chemistry 101 and put it in and do some funny business. So yeah, I mean, it's an unanswered question.
Iron in the silicate was studied with Paul Asimov's work on the shock wave studies of the liquids, but FeO is still an issue.
Yeah.
So they had some work on the FeSiO3, MgSiO3, diopside jadeite joins, and constructed based on shock wave studies to extract alpha-free energies.
Yeah, so that's a very good point. So how do you get this data? Static studies, right? Like squeezing things, Birch-Morahan equation type stuff. Shockwave studies, which in the U.S. I think that Caltech is pretty much the only guys doing that. As far as silicates.
Right, for silicates.
Yeah, for silicates. I mean, other people do it all the time. Bomb guys have been doing it for years. Shockwave, and then I think with the lower mantle, I think molecular dynamics is coming into its own. Yeah.
But also, as with the Ghiorso modeling, there's also phase equilibria constraints that are progressively being generated as well on the thermodynamics of the system. So we actually are starting to have a concept of what's the solidus, what's the liquidus phase. That's admittedly in a very nascent state, but that phase equilibria data is a very fundamental input to the Ghiorso modeling, for example.
Yeah.
So that's the additional parameter constraint that I think often mineral physicists slightly forget.
Yeah, good point. Yeah, so I'll try and wrap up here. I definitely will finish on time. And so this crowd knows this, but I guess it's a bit of a tutorial. Maybe people haven't been through this. So we want to think about temperature gradients in the mantle, specifically of liquids moving up or down. And how do we go about this? Well, the time-honored way is to consider that in a convecting system, the temperature gradient falls along the isentrope. And how do you actually derive that for a single-phase material? It's something like this. So you have an entropy. You break it up at fixed compositions. You don't have any X terms here. Temperature derivative, pressure derivative, basic thermodynamics, ds dt constant P, Cp over T, minus alpha V, expansivity, volume, and set ds equal to 0, and fool around with this a little bit, and out falls the isentropic gradient. And you relate pressure to depth, obviously, through something like that. And so then you end up writing dt dz at constant S, looks like alpha T G Cp. Yeah?
Yeah, just going back to a previous question, if I had written that dt dps equation, I would have put on an additional equal sign that would have said is also equal to the Grüneisen parameter times temperature divided by bulk modulus. So for the adiabat. So this is the difference between low pressure people and high pressure people.
Yeah.
Is the Grüneisen parameter is about equal to 1. So that's why why we keep talking about Grüneisen parameters is that we can put in a factor of 1 there, and then the adiabatic gradient is the ratio of the temperature to the bulk modulus, both of which we know, as opposed to all these messy thermodynamic parameters like heat capacity and thermal expansion.
Okay.
So that's the real utility of the Grüneisen parameter.
I think on the next slide I may write this in terms of...
Oh, I'm sorry.
Yeah. Yeah, the Grüneisen parameter is nifty because it's roughly a constant. Changes the pressure and temperature. And at the next level, it depends on volume, not so much on temperature. And then at the next level, it depends on the whole. And then composition. Oh my God, now you're really screwed. But it's a nice vehicle. Anyway, so typical isentrope here is 0.3 degrees per kilometer. Just putting in some typical values for silicate solids. And I'm not going to really go through this. You can think about magma ascent in cracks and pipes. You can worry about this kind of stuff. It's not really isentropic ascent, right? Because you have the possibility of heat transfer. You have friction that could be degrading mechanical energy into heat. And there's standard ways, and I think Michael talked about this yesterday, because he was talking about the mantle, conservation of mass, conservation of momentum, conservation of energy. This is written for a fluid in a crack, okay, that's moving up, say. The only point I wanted to make here is that it's interesting that when you look at this, it turns out that this coefficient that modifies the pressure gradient is actually something that falls out of classical thermodynamics. It's actually the Joule-Thomson isenthalpic relationship between temperature and pressure that's actually equal to that. So it's kind of interesting. Anyway, if you neglect changes in kinetic energy of this fluid in the crack, and you don't worry about heat transfer, and you say there's no friction, then we're back to kind of the isentrope. And you can examine the one-dimensional sort of energy equation. This is an enthalpy change, kinetic energy, gravitational potential, heat absorbed, and the non-pressure volume work. And you make all these classic assumptions about neglecting, it's adiabatic ascent. Heat does not leave the pipe. You don't worry about friction. It's small anyway, but it's there. And you can derive a relationship between the temperature, the depth, and the fraction of liquid. So you start with a diapir that's just kissing the Clapeyron slope. It's just starting to melt, right? And as you continue to decompress it, I think I have a picture of this. It then follows the Clapeyron, right? So here's the deal. You've got the parcel of whatever, Taco Bell, or it could be real prototype, and it's rising, okay? And so this is its temperature gradient in a convecting system, previously convecting system. And it's rising here. This line is the Clapeyron slope. This is the melting curve. So if this was diopside, it was a diopside planet, right? Exoplanet diopside, all calcium, magnesium, silicate. Then this is the melting curve for diopside that started this lecture, right? That's what this is. Continuous and the dash. That's the Clapeyron slope. This comes from thermodynamics. It doesn't have a damn thing to do with anything else. The adiabat comes from the real Earth. It's the actual temperature gradient of this parcel that's moving up. This parcel of solid dioxide. And so it comes up here, and the isentrope intersects the Clapeyron slope because the isentrope is steeper than the Clapeyron slope. Typically, at low pressures, the Clapeyron slopes are like this. Adiabats are steeper. So it's inevitable something coming up here, unless it was starting here, is going to intersect the melting curve, right? And it intersects here, fraction of melt is 0, and it stays along the Clapeyron, solid in equilibrium with liquid, increasing the amount of liquid as enthalpy is converted, right, from the pressure effective enthalpy, taking that difference and putting it into latent heat. I mean, that's what the equations tell you. And then at some depth, you segregate that liquid from the solids, and then the liquid comes up on its own adiabat, which is a little bit steeper than the mantle adiabat. So that's like the canonical decompression melting, right? That's how it works, right? You've got some melting curve, solid is the prototype, you have the stuff rising beneath Samoa, and it intersects the Clapeyron slope and it melts, and it does that. But, and this really will be the last things I say here, you can get some really cool things going on here when the isentrope and the Clapeyron slope become very, very similar. You notice in that low pressures, they're very distinct. But what about when the Clapeyron slope goes negative? Whoa, that's crazy, right? But it does happen. How is that going to relate to melting on a super Earth? And how do we deal with stability of liquid layers? So it really comes down to saying, how does the melting temperature depend on depth, right? That's really what we're talking about. And as Quentin just pointed out, here's another way of writing the isentrope with his favorite number, the Grunison parameter here, right? And I think that's the isentropic modulus, right? Yeah. So this is Ks instead of Kt. Not a big deal, but to be correct. And this is log T, so there's a T over here. But anyway, this is the deal, and this is what's really cool about it. The high pressure electrodynamics, either done by classical MD or done by first principles MD, show that in liquids, this thing actually increases along an isothermally, as pressure increases. Right? So this is getting steeper. Right? But when you look at melting curves, just empirically melting curves, going back to Bridgman and people like that, and I'll show you some examples here. Remember that the melting curve is basically delta V, the volume change between liquid and solid, right? Liquid and solid, and the entropy change. Well, this thing is always positive. I mean, when you go from a solid to a liquid, there's an increase in entropy, right? You don't have to be that smart to figure that out. Even Donald Trump, well, no. Okay, but the really cool thing is that delta V here, which is basically saying, is the liquid denser than its parent solid or less dense? That actually can go to zero and actually can be negative, right? I mean, ice and water, right? So this is just, the top one is just to show you that Granissen parameter does depend on pressure, especially up to about 30 or 40 GPa. But what I really want to leave you with is show you just some melting curves for some silicates and some other compounds and show you that they really do flatten with depth. So meaning that the Clapeyron slope and the adiabat are becoming more nearly parallel. And I think you can get a big region with low degrees of melt if they're touching. So here is, God knows what this is. Okay, this is calcium. This is basically perovskite. And here's a melting curve. So this is temperature, this is pressure. So, at low pressures, where we worry about things, magma generation and Great Basin and all that groovy stuff, we're just here. We're pretty damn straight. But higher pressures kind of curves. They do flatten. Why? Because delta V, in the numerator, delta V over delta S, delta V is smaller. Right? As you go to higher pressures, the volume change gets smaller. Entropy change, it changes, but it's pretty much a finite positive number. So I'll show you a few others. Here's from the old days, Boyd in England, diopside melting. Right? This is actually in kilobars. This is 8 GPa here. And you can see a little bit of curvature. Right? Okay. But let's go to some more robust study, more recent studies. This is calcium, aluminum, perovskite, right? CaPV, right? And this is, again, temperature. This is pressure. Here's core-mantle boundary. And look at this thing, and these are data. This is a fit and blah, 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 but these are the data. Clearly, this melting curve is flattening, right? And then to really, really blow your mind, this is selenium. And many elements actually do this. You can go find out a little compendium on melting curves of all the elements that physicists have done and mineral physicists have done, and many of these things flatten. Right? And some of them, I don't know if I had one here, but some of them actually turn over. Yeah. So this is melting of sodium. Okay, now I understand it's not made of sodium, but actually turns over. The Clapeyron slope goes negative. So somebody here in the workshop should think about the adiabats and the Clapeyrons and what happens when the Clapeyron is negative with an adiabat. Do you ever get melting? Will those melts ever come to the surface? So I have 1 minute left, and I'll just talk about.
I'd like to save some time for discussion.
Yeah. Okay. Well. Okay. There were a lot of questions. I guess. I'm willing to wrap it up. I got to do one more thing. Okay. So here's a hypothesis, conjecture. Right? When we do these ND experiments, we notice something. Right? We go to really high pressures. We notice that the beautiful thing about ND is that you could look at the structure of the melt. So you could look at, for instance, an oxygen and say, this oxygen, how many next nearest neighbors of oxygen does it have? You could ask it about how many nearest neighbors of magnesium does it have, of silicon, whatever. You got all the data there. You know in Euclidean space the location of every atom of your 100,000 atoms, and it's easy to figure that out. And so keep that in mind, and keep in mind that silicates are 90% by volume oxygen. Okay, they're basically they're packed oxygen spheres, repulsive spheres. That's really what a silicate is. 90% by volume oxygen. Forget about all the other stuff, right? Okay, and what this plot shows is a packing density as a function of coordination number. And it shows the things we all know. Why are silicates based on tetrahedral packing? Well, because that's a local maximum in packing efficiency. This is 4 tetrahedral. Why do we have stishovite with silicon and 6 packing with oxygen? That's another efficient way to pack charged spheres. Right? 6. This is 6. The granddaddy of them all is icosahedral. It took me a couple of weeks to learn how to pronounce that. It's the granddaddy of them all is icosahedral packing. That's 12 packing. That is a classic Platonic polyhedron, right? Plato knew about it. It's the most efficient way. And what this shows is the packing density versus coordination number for packing of equal size, oxygen, spheres, around a common center where there are intrinsic repulsive forces. Oxygen's -2, right? And it shows that this is like a really efficient way to pack oxygen, 12-fold. And if you look at this, and don't worry about this, this is MgSiO3 liquid. It's one empirical potential that we ran, and another empirical potential by Oganoff that we ran in MG. And I think there's even some large stuff in here somewhere buried, or maybe not, I forget, it's in the paper. But notice this dashed line and the dashed blue line is the average coordination number of oxygen around oxygen. And what we noticed was that it grows and it becomes quite large. So 35% of the oxygen around oxygen is in this coordination number, right? High, 18 at this pressure. But at a critical pressure here, for 2 empirical potentials and 1 first principles, we see at about just above the core mantle boundary, we see this change from very high mean coordination number, right, to this limit of about 12. Right? And so the speculation is that, well, maybe, the old guy upstairs gave us something. Maybe we can use this idea of this packing limit. Maybe it will help us understand the nature, the properties of melts along core mantle boundary. Maybe this icosahedral packing of oxygen can be utilized in some way. Maybe it's going to simplify the thermodynamics. Maybe it's going to simplify the mixing properties. I don't know. But it's just really interesting to me that works at high pressures, and that it seems to kick in, at least for MgSiO3, right, pretty darn close to the core mantle boundary. So I should stop there.
Thank you. Have some time for some discussion, even though it's coffee break time. Dorn?
I have sort of a question I've always been a little bit confused about, which is that most of the geodynamic models show mantle convection systems where it's not really adiabatic, it's subadiabatic for large volumes of the flow regime. Do we need a correction for sub-adiabaticity for the thermodynamics, or can you get by just treating everything along an isotrope?
Yeah, you make a really good point. I think the isentrope is without radiogenic heating, right? So probably Michael would know more about this, but that's quite true that in systems with radiogenic heating, is the isentropic limit still valid, or is there a correction that comes there? I don't know, but I suspect you would want to think about that. Because the adiabat really just says, it's the temperature due to the self-compression. Right? That's really what it is. You're decompressing, you're expanding, you're taking pressure volume work, and you're doing pressure volume work, and that relates to the temperature through the constant entropy. But if you're generating heat, right, it's not a constant entropy process. So does that steepen or does that make it shallower?
It shallows in most of the dynamic models, so the question, it's going to inhibit melt.
Yeah.
You're diverging from the solid.
Yeah, good point. Yeah, especially if the clap run comes around, it goes this way.
Yes, Quentin and Dan?
Okay. Just a comment on Thorne's question that, I mean, you guys do have a measure of this, which is the Bullen parameter, which has been widely, I won't say forgotten about, but it has not been belabored. But that is a measure of the seismic deviation from adiabaticity, which I would regard as I don't want to say anything disparaging about geodynamics, but that's an actual potential, although coarse, measure of deviations from adiabaticity.
Dan?
Yes, I have a question about your last slide. I was very intrigued by that oxygen coordination number change in the melt. On the other hand, Jennifer yesterday nicely showed that the oxygen volume decreases a lot faster with pressure than the cations because oxygen is inflated because it gains the electrons, so it's a lot more compressible. Whereas cations, they have lost their electrons, so it is very difficult to compress them with pressure. So what that means is that the relative volume contribution from oxygen decreases strongly with pressure. In that case, cation influence on the melt properties and packing density increases with pressure. So wonder if that has been included in your simulations or not.
Well, the MD results are just that. You have a potential, and you put it in the composition, and you do MD, which I'm willing to talk about, which I've been doing for 15 or 20 years. And what you see is what you get. And then we go in and we look at the structure of the liquid. We have the locations, and then we do the coordination statistics. We take all the silicons and we say, here's a silicon. Let's look at the next nearest neighbors of magnesium around that silicon, and the oxygen around that silicon, and magnesium around that magnesium. And we do that for every atom type in the system, 200,000 particles, and do that systematically as a function of pressure. And that's where you see that drop, that's a mean coordination level. So that's not, that just falls out of the simulation.
I think one more.
Do you fit your empirical potentials at heat pressure?
I'm sorry, say that again. I have a hearing deficit.
You are using empirical potentials in your molecular dynamics.
Oh.
So are you fitting them at each pressure, or are you fitting them at one pressure and using them?
A little bit of both. These results were the straight out of the box. So one potential was from Matsui. So he gave us the potential parameters. He wrote about that. And the other was from Oganoff. And so, we take those as the handed down word and then run the MD. So the Oganoff potential is probably, it has a little more chemistry in it, I think, in some ways. And I was talking to Lars about this the other day, and in their first principle molecular dynamics, which doesn't use a classical potential, that's really the way to do the problem, because you solve the electronic problem essentially every step of the molecular dynamics way. They see this drop in that oxygen coordination result. The problem with first principle molecular dynamics relative to classical is in first principles, you're more or less practically really limited to about 100 particles. Maybe 150 if you've got a huge computer budget. And you're limited to maybe 10 picoseconds of fluid time. In classical, this is where we were in classical when I started doing ND in 1980. Now we could do 300 particles and do it for 30 picoseconds. But now we can run hundreds of thousands of particles. You know, our cells are huge. And we can run it for nanoseconds. And that's not so important to get thermodynamic properties, because believe it or not, in 10 picoseconds you can get pretty good ones. The problem is in getting transport properties, like thermal conductivity really requires very long runs, right? Because the correlations are noisy and blah, blah, blah. And so you need long runs that do really good transport properties. And to do these structures, I mean, if you have 100, you know, MgSiO3, you have 90 particles. You know, you've got 12 silicons. How the hell are you going to do good statistics on the coordination of that? You know, with so few numbers. It's difficult. You know. Whereas when you're running hundreds of thousands, you obviously get much better statistics. You have much more data to work with. But you're using an empirical potential, and you're not really doing the quantum mechanical problem of solving electronic structure. So what we do nowadays is we have the golden spikes, have some first principle MD results, and then we jockey around and develop effective pair potentials that more or less recover that. And that's usually it's very successful. And then you could go on to thinner ice. It's thin ice, but it's not like a nano layer of ice. It's you feel confident because you can actually reproduce the first principle stuff. So yeah. Okay. So I think for mineral physicists here, get into doing first principles and classical molecular dynamics on silicate liquids, because it's not touched. I mean, it's just barely touched. It would be a great thing for people to do. Because if we did enough canonical compositions, then you could build a model for the free energy of liquids at core mineral boundary pressures and temperatures across a wide range. 8 components, 10 components. Silica, alumina, titanium, magnesium, iron. And then you'd have the data to do the Gierso problem, but do it for the lower mantle. Right? So that's a labor of love or a group. But I think if it was a concerted effort with good computing time, which is very available now, probably could do that, I'd say, in half a decade, probably, if there was a group of 10 or 15 people who got together and decided to do that. And I think you'd get a lot of bang for the buck if you did that. Anyway.
Okay. Well, thank you.
Yeah.
I think we'll break for half an hour.